Hi there, in this video we're going to look at the symmetries in the Fourier transform. So what we're interested in doing is looking at the even part of a function and the odd part of a function of time and seeing how this even and oddness maps into the frequency domain, and also we're interested in the imaginary and real part of the time and see how that maps into the frequency domain. So we're just looking at the various symmetries that will arise, okay, from the Fourier transform. So let's start off with an even function. So we know that's an even function because if we took some value of t, then we could find a value f of t there. So that's f of t. Then if we went to minus t, then we found f of minus t, where we get the same value. Okay, so that's a definition there of an even function when f of t equals f of minus t. So let's now look at an odd function. Now I've drawn an odd function out here, and if we look at some value t, then we could find a value g of t here, which would be this point here. Now if then we went to look at g of minus t, well that's minus t there, so g of minus t would come down to here, so that would be the negative of g of t. So then we could write then g of t equals minus g of minus t. So equally we could take that negative across here as well. We could write minus g of t equals g of minus t. These are equivalent. So this is the definition of an odd function. Now what we're interested in is interested in the multiplication of an odd and an even, of odd and even functions. So we're going to do a little proof down here, and we can see that even times even will give you an even function, and odd times odd will give you an even function, and odd times an even will give you an odd function. Okay, so if we were to imagine f of t and g of t were both even functions, so we're doing the first one here, then what we could say is f of t would be the same as writing f of minus t, and g of t would be the same as g of minus t. So if we were to multiply f and g together, we would have h of t. Okay, and again we multiply f and g together, this would be h of minus t. So we would have h of t equals h of minus t, which is the definition of an even function. So an even times an even will give you an even. Okay, so now if we were to look at an odd times an odd, so f of, let's say both of them are odd functions, then f of t times g of t would be, we could write the odd function of t is of f is minus f of minus t, and the odd function of t is minus g of minus t. Okay, the two minuses cancel out, and then when I multiply these two together, let's say it gives us h of t, then when we multiply these two together, this would give us h of t, but it's h of minus t. Okay, so again we would have the combined function h of t would be h of minus t, which is an even function. Okay, so an odd times an odd is going to give us an even as well. So the last one, if we were to imagine f of t is even and g of t is odd, then when we multiplied the two together, we get some function h of t. So we could write this here as the even function, we could write as f of minus t. The odd function would be minus g of minus t. Okay, so we can take the minus sign out, so with minus sign out, and we'd have g of minus t, f of minus t. So that means that h of minus t is the minus, and if we multiply the g and f together to give us our combined function h, it would be h of minus t. Okay, so that there is the definition of an odd function, which you've seen above. So an odd times an even would give you an odd function. Okay, so now if we were to look at the Fourier transform, so there's a forward transform there just written out. Now what we're going to be interested in is we're going to be interested in taking this function of time and splitting it into even and odd terms, and we're also going to be splitting the even terms into real and imaginary, and the odd terms into real and imaginary, and we're going to be doing the same in the frequency domain, and we have to equate each of them just to see which one is equal to the other. Okay, now another thing here is that we notice we're integrating between minus infinity to infinity. So if we had an odd function, so there's an odd function of time, so if we integrate an odd function from minus infinity to infinity, we get 0, because you can imagine this area here would cancel with that area, this area would cancel with that area, so all the areas would cancel with each other, okay, so you get a value of 0. But if we were to look at the integrating an even function from minus infinity to infinity, then we could say that area there would cancel with that one, so this is an even function, this is a cosine function, right, that would cancel with that would cancel with that, so on and so forth. But the one in the middle here, there's nothing for it to cancel with, so there would be a value, so the integral from minus infinity to infinity of an even function does not equal 0. Okay, so let's start splitting this function up. So we're going to split the function of time into an even function of time and an odd function of time. So we're just writing out the Fourier transform again, and we're taking an even function of e to the minus j omega and an odd function of e to the minus j omega. Now minus e to the minus j omega can be written as cos omega t minus j sine omega t. So it means that in essence we would end up with 1, 2, 3, 4 terms. But the reason for showing you this up here is that we know that when we integrate odd functions over infinity we're going to get 0, okay? So if we look at this thing here, that's going to be this thing here, that's going to be an even times an even function, which will give you an even function, so there will be a value there. That's an even times an odd sine omega t, so an odd function, so that's odd even times odd, which will give you an odd function. So it means that when we integrate that from minus infinity to infinity we'll get 0, so we'll cancel that one out. And the same this end here, if we look at an odd function times an even function will give us an odd function, so that will cancel out, and that will be an odd times an odd, which will give you an even, so that will be an absolute value. So it means that by splitting the time function into odd and evens, we know that we're only going to end up with 2 of the terms left, so those are the 2 terms there. So there's the even part of cos omega t and the odd part of sine omega t, because this here is going to give you an even function and a real and a value, and that's going to give you an even function and a value as well. Okay, now what we're interested in is in the frequency domain. The frequency domain as well, that's going to have frequency domain is going to have a real and an even part of frequency. It's going to have an imaginary and even part of frequency. It's going to have a real and odd part of frequency and an imaginary and odd part of frequency as well. Okay, so we're interested in these 4 terms. We're interested in how these 4 terms map into the time domain and vice versa. So let's have a look. We can go back to the Fourier transform and we'll take our real and our imaginary part of both of these. So we're going to end up with 2 terms for this and 2 terms for that. Okay, so let's say we'll take the real even part of time. So that'll be the real even part of time, which is the first one here. Okay, and then we're going to take the imaginary even part of time. So we're going to take the imaginary part of this. Okay, so that's going to be plus j, imaginary part of the even part of time, which is this one here. Okay, and then we're going to take the next one there, which will be the real back there. We're going to take the real odd part of the time. Okay, so that's the odd part, so we're going to take the real part of this. Okay, so that's going to give us our minus j. Okay, that's minus j there, and it's the real odd part of this. Okay, and then the last one we're going to take the imaginary odd part of this. So the imaginary odd part of this, well, the j's, the 2 j's will cancel. Okay, because it's going to be the imaginary odd part of this, so it's going to be j times j, so it'll be root of -1 times root of -1 is negative, and the negative there will disappear as well and give us a positive, so we'll get a positive value here. Okay, so just go through that yourself again and convince yourself. Okay, so that will be as seen here. Okay, so it means we've got our 4 terms here. Okay, and we've got our 4 terms here, and we have to equate these 4 terms with these 4 terms here. Okay, so the first one's easy enough. The real even part in the frequency domain, okay, is equivalent to, well, it's the real and even part in the time domain, and the imaginary even part in the frequency domain is equal to the imaginary even part in the time domain. Okay, so we've ended up with these two equations, equation 1, equation 2. So what we're saying is, if you've got a real function, a real even function of time, when you do the Fourier transform of it, you'll get a real even function of frequency. Or if you've got an imaginary even part of function of time, you'll end up with an imaginary even part, imaginary even function of frequency. Okay. Now the next two are different because they're swapped round about. Okay, so what we're interested in is the real odd part of j omega. Okay, so we're interested in the real. So the real part is not the j part here. The real part is this part here. Okay, so we're equating it with this here. So that's the real odd part is equal to the imaginary odd part. Okay, of sine omega t. And again, we're looking at the imaginary odd part here. Okay, so the imaginary odd part here, well, the imaginary odd part of this is this part here, because that's the imaginary. Okay, so the imaginary odd part is this here, is the real odd part in time. Okay, so we can end up with these two equations here, where we can say that if you've got an imaginary odd part of frequency, imaginary odd function of time, whenever you do the Fourier transform of it, you get a real odd part. And again, if you had a real and odd part of time, when you did the Fourier transform, you'd end up with imaginary odd part of time. Okay, so these are the only two awkward ones. They're swapped round about. Just have again another look at that to convince yourself if needs be. Now, one last bit, what I'll do is just the actual drawing. Okay, so it's just a little graphical representation. Okay, so I hope you can see this right. What we've done is we've taken each of the four from the previous page and I've just equated them, so that drawn them out. Okay, so the first one really is saying that if we were having a real and an even function of time, so there's a function of time, it's real, that's the real axis, that's it's an even function of time. We'll map it through the cos omega t and we'll end up in the frequency domain, so that's omega is the frequency domain, we'll end up with a real and an even function of frequency. So I've drawn that little sinc function in, and that's a purely real and even function. So we're interested in that one there. Next one we look at, again, it's an even function, but it's an imaginary function of time. So we've got an imaginary axis there, so that's our time axis, right? But we've got an imaginary time axis, so that's an imaginary even function. Again, it's going through the cos omega t surface, but we're ending up with an imaginary even function of frequency as well. Okay, so that's the frequency domain, that's omega, the real part of frequency, and that's the imaginary part of frequency in this axis. So we've got an imaginary even function of time. Okay, and the third one there, if we're looking at an imaginary odd function of time, so that's an odd function and it's in the imaginary axis of time, and when we do the Fourier transform, we're working through the sine omega t surface, which is the odd surface because it's an odd function, and it's going to give us in the frequency domain a real and an odd function of frequency. Okay, so that's just the real axis of the real frequency axis. Okay, so that sits up in that axis. And then finally, if we looked at a real odd function of time, so that's a function of time there, that's a real function of time, we would go through actually the sine, be a sine minus omega t surface, and this will give us an imaginary and an odd function. So that's an odd function of frequency and it's in the imaginary plane. Okay, that's the imaginary plane there. Okay, so it's sitting in that imaginary plane. So we ended up with these four examples. Now the only two really we're interested in for now is the real functions of time. We're not really interested in the imaginary function of time. So what you can say is a real even function of time will give you a real even function of frequency, and a real odd function of time will give you an imaginary odd function of frequency. Okay, so those are the only two we're interested in. I don't think there's anything else I want to say on that. So that'll do for now. We'll go through in another video. We'll go through a few more examples of these, and you'll see the usefulness of this. Okay, so thank you for listening, and goodbye.